Hi, I'm Neeraj, and I'll be talking on to the commit log internals. Yeah, it work. At the end of this talk, I'll give a small bio. Level agenda is I'll give a brief introduction about what commit log is, where it helps, how it is structured, how the logs are stored, how it interacts with other Postgres components like MVCC and Val, and we'll just deep dive into how exactly it operates, how the commit actually happens, what optimizations are in place, and things like that. Okay, so at a high level, if you had to imagine, this is what a commit logs page would look like. Okay, all these blue boxes, 4 bytes in size, and as I mentioned, commit log plays a role in implementing the MVCC, which is basically your Postgres' concurrency control mechanism. So instead of locking all the rows where the transaction is going, there's a snapshot which takes place, and on that the transaction happens. So that's MVCC. Other than that, it also helps in crash recovery. Guaranteeing that if something goes wrong, your database node fails, all the transactions which were committed, they just remain there. Okay, there is no data corruption. And we can also imagine that commit log loves cats. It's not proven, but yeah, we can imagine. Okay, so from the structure side of things, the commit log is of 8 PBs in size. Okay, and all of these blue boxes, they are just 4 bytes in memory. For each log, it only takes just two bits of memory. Okay, all these logs, they start from 0 and they are stored into PG exact directory. Around Postgres 7, it was stored in the PG transaction directory, but since 7 and above, all of this is stored in PG exact directory. Okay? So these transactions, they have 4 states. By default, all the transactions which are logged, it's in progress. Okay, so status is just 0. Committed transactions, they go with status 1. If a transaction is aborted, it goes with status 2. And all the subcommitted transactions, they go with status 3. So the subcommitted transactions are those that you have a statement which says begin and you have end, and you have multiple statements, inserts, updates, deletes. Okay, so you have one transaction which sits at the top, and then you have sub transactions. So the parent transaction, it goes with status committed, and the intermediary, all the sub transactions, if they are committed, they are called the sub committed transactions. Okay. Any questions till this point, or I can proceed? Okay. Yeah. So all the commit log pages, they're 8 KB of size, and since it takes 4 bytes, it's represented as 4 bytes. In all, you can have 32768 transaction IDs which are maintained in the commit log. Okay. And if you have noticed that there is no transaction ID to commit log status mapping. Okay, so you can imagine. I'll just go brief into how this is maintained. But you can imagine that this is a hash map, this is a 2-level hash map, where all the keys are guaranteed to be unique. So it doesn't make any sense to store the keys. Okay, so that's how the space is also optimized. Okay, and the commit log, it's flushed very periodically, but specifically whenever a transaction calls checkpoint, it is actually pushed to the disk explicitly. And whenever database is being shut down, just to keep things really very consistent, all the pages along with the commit log pages, even they are also flushed to disk. Okay, so now we'll just talk very briefly about how a transaction is mapped to a commit log page. So in Postgres, my transactions, they start from 3 and they go all the way up to 2 to the power of 32 minus 1. Okay, 0 is invalid transaction, 1 and 2 transaction IDs, they hold a special status. So it starts from 3 and goes all the way to 2 to the power of 32 minus 1. Okay, so whenever a transaction comes in, we need to do 2 things. First, we need to see that on what commit log page this transaction will live. Okay, and it's actually quite simple to find out. we divide the transaction ID by the page size multiplied by 4. Okay, so once you multiplied by 8. So if you do that, we will see that. Say for example 1957860. If I apply this formula to this, I'll get to know that on what page my transaction should go. Okay, so that is one level of mapping. Secondly, within this page, what exact integer will store this transaction? Okay, so again, it's quite simple. Transaction ID modulo by how many transactions could be present in a page divided by my byte size. Okay, so eventually, in my first step, for 1957860, we decide that it goes to page 59, and then we apply the second formula, which says that what exact integer my transaction is going to live like. Okay, from there on, we just do some real bit manipulation wizardry to set or unset the value. Okay, so again, so as I mentioned earlier, you can imagine this to be a hash map with two levels of mapping. Level 1, the page. Level 2, where inside the page, 8 KB of page size. If you have to actually really visualize this is how actually you can visualize this. It's a page with 4 bytes of memory. Okay, you put something over here, and periodically it gets flushed. Okay. Again, this is a SQL. You have to guarantee the atomicity. So there is a really good algorithm which is in place. To just kind of balance out between performance and does that answer your question? Yeah, please.
From within the PT kernel code, how do I get access to the
Yeah. So if you want to look at the source code, right, that what actually exactly. Yeah. Okay, so the starting point should be CLOG.c. Okay, there you can find all the details about the structure and everything. Okay, there is one method. So if you want to start for the entire life cycle, go to the method startup CLOG. Okay, and if you want to see that how exactly the things happen when the commit takes place, go to transaction ID set page 3 status. Okay, so actually this is in my slide references. So from there on, you can follow the life cycle, that how it exactly finds out that what SLRU bank I am supposed to go, how it locks, and things like that. Thanks. I hope I was able to answer your question. Okay. Any other questions? Yeah. Yes. So usually 4 byte is my natural granularity. Okay, 2 raised to 32 minus 1. I mean, you really need just 2 bits of memory. But if you see that in terms of CPU, everything at least starts from byte. Okay? I can't just go ahead and manipulate byte just to keep things really simple and very efficient. Let's go with 4 bytes of memory. Okay? Yeah, that's it. Okay, so how does CLOG participate in MVCC? Okay, so a real quick refresher. So MVCC is the concurrency control mechanism of Postgres via which multiple transactions can work on a single row without it having to lock the row. Okay, so how MVCC works is whenever a transaction starts, all the rows which are part of the transaction usually takes a snapshot of it. Okay. All the updates, they happen on a snapshot, and finally the snapshot is committed. In the meantime, if the snapshot is really not committed, it's not consistent, there is some inconsistency, then the transaction is rejected. Okay, but this is very easy, lot-free ways of doing things. Okay, so this is essentially just snapshot isolation. That's how PG implements this. Okay, so how CLOG comes into picture over here. Okay. So, as I mentioned that whenever my MVCC, whenever transaction starts, my snapshot is taken. Okay. All the transactions which were committed before this, my transaction started, they are visible to this snapshot. Okay. So in this diagram, my snapshot started, and I was assigned my first transaction ID was 937. So all the transactions which happened before this, they are visible to me. Okay, the transactions which were in progress or which committed when my snapshot started, they are not visible to me. Okay, so how do I even decide, that what transactions are committed or what not? There is information in the tuples, but another way to look forward to look into this is commit log. Okay, so PG, it goes, it takes the snapshot, it sees all the rows, all the transactions which are a part of my snapshot. It goes to CLOG and it sees that whether this transaction has been committed at that point or not. Okay. Once it gets that information, it also caches it because it's not really efficient to go to a different directory, to go to a different page and do a lookup. So that information is persisted as well while the transaction is in progress. Okay. So essentially, yeah, this is where the commit log helps. It gives information to MVCC that these are the list of transactions which have been committed. Okay. Any questions over here? Okay. Secondly, commit log also plays a significant role in crash recovery. Okay. Let's see how. So Postgres has this very legendary mechanism of doing the updates. The write ahead log. All the inserts which were come into my system are put in a sequential order in a write ahead log. Okay. So basically all my updates, they are given a logical sequence number or LSN just for short. Okay. The way in which the commit happens is first my row is flushed to LSN. Okay. Secondly, once this row is flushed, the status is written in the commit log. Okay. Once both of these things happen, I can say that my transaction has been committed completely. Now, for example, something was flushed to val, but it wasn't flushed to CLOG, and my database restarts or my load fails. So whenever the crash recovery happens, from the crash recovery's point of view, commit log is the source of truth. If something is there in val, it is not in a commit log, it is considered to be an aborted transaction. Okay, so that's how commit log helps in crash recovery. So this is for what it's called as a synchronous transactions. Postgres also has a notion of asynchronous transaction. Okay, so how this happens is you do a transaction, you tell Postgres that this is an asynchronous one. So Postgres will take this transaction, but it won't commit it. It will batch them all together. Okay. So in that case, see what happens is there could be a condition where a flush is being done. It can end up into commit log first and then into val. Okay, and if at that point, if my database crashes, then there will be information in CLOG but not in val. So how Postgres deals with this situation is, during the time of CLOG flush, it checks whether this transaction is asynchronous or not. It's just one if condition by which it's checked. It's actually quite efficient. If it is, then it waits for val to get flushed. And once val is flushed, after that, the commit log is flushed to this. Okay, so that's how for synchronous and asynchronous transactions, atomicity and all of these things are guaranteed. Any questions over here? Okay. Okay. Now, so we'll deep dive into how exactly the transactions are committed. Okay. So for this exercise, assume that we have T0 to T5 transactions which are being committed. And it so happens that T0, T1 and T2, they are on page 1. T3, T4 and T5, they are on the second page. Okay. Here T0 is my parent transaction and T1 to T5, they are the sub-transaction. Okay, they all belong to just one begin and end statement. So now how this will be handled, let's see. So first of all, the first step is take all the transactions which belong to one page and start flushing them. Okay, and we start from the bottom of the tree. Okay, first step is to subcommit all the sub-transactions. So in our case, T3, T4 and T5. So all of them, or all the byte offsets belonging to these transactions, they will be set with status 3. Okay, which says that this is a subcommitted transaction. In that step, we atomically commit transactions T0, T1 and T2. Okay, and as the final step, we commit transactions T3, T4, and T5. Okay, and now at this point, my entire transaction is committed, and it's also flushed to the disk. If it's optimal to do that. And again, this is the async behavior, which I've talked about. So, so the general behavior is all the transactions which belong to a page, flush them first. If they're part of a sub-transaction, then flush the sub-transaction first, and then the parent transaction. Okay, so this is kind of like very edge casey kind of a path. Most of the times, all the transactions generally they belong to the same page, but every now and then it can happen that my transaction ID is really very large, and like this kind of overflowing pages. Okay, and also see there is no limit to the number of transactions you really can do. So it is possible that somehow someone managed to write a query which has like almost 100,000 or so transactions. So Postgres will be very happy to take this, and this is the mechanism by which the consistency will be guaranteed. Yeah.
Any questions in this part?
Okay. So see, we talked about how the transaction is being flushed. But if, let's say, for example, if we take a very naive approach, that whenever transaction comes in, we bunch them together and flush them to the disk, then this is actually going to impact my disk, my I/O, actually my performance, because disk I/O, even if you're on SSDs, it is the slowest piece. Fastest is writing onto the memory, then comes the disk, and finally, the network communication. So in order to optimize things, Postgres uses some heuristics. Okay. So the heuristics are, if I have a number of transactions which are less than 6, they all belong to the same page, then let's do it this way. So again, this is my SLRU, simple LRU page, okay, and it is possible that multiple transactions are trying to write on the same page. So what will happen is, if this condition is met, Postgres tries to acquire a weightless lock. It just says and then checks with the SLRU that, hey, can I just go ahead and just write it to this page. And if SLRU says that no, the transaction is progress, no other transaction is trying to write onto this page, it just gives out the lock. Okay, so there is no wait in this case. If the lock is acquired, then this is how the things will be flushed. Go to the find out the page, find out what bytes we need to commit, and flush it onto the disk. Okay. Say for example, this does not happen. We were not able to acquire a weightless lock. Okay. So in that case, what will happen is Postgres will try to perform a group update. Okay, we'll see what a group update is in a little while. Okay. Assuming that the conditions in part 1 they haven't been met, the number of sub transactions were less than 6, were actually more than 6, or they didn't belong to the same page, then commit lock, it will try to acquire a sleepy lock that it will take some time to get the lock and then perform the updates. But then again, the update sequence just remains the same. Okay. Now we might ask that why the number of sub transactions have to be less than 6. Okay. Now, what I found out from the old PG hacker mails is that numerous benchmarks were performed. It was observed that the performance is extremely optimal when the transactions are less than 5. For more than that, there were actually some of the other bottlenecks, so it wasn't really making sense. And I believe Amit was the guy who actually did that. So yeah, we have a legend between us. Okay.
Any questions on this part, or we can move to the optimization?
Okay. Now we'll just see that what exactly happens when we are not able to take a sleepless lock and how the group update is performed. Okay. So what happens is in Postgres, all the connections they are represented by one process. Okay, Postgres actually follows that model, just like Google Chrome or Brave. It has its cons, but from the security and some other perspective, it has its own benefit as well. Okay. So here, the process which is trying to update a page, it sees that are there any other processes which are trying to update a transaction in that exact same page. Okay. If there is a process which is trying to do this, then what it will do is it will insert itself into a list. Okay, that I'm also the person, and these are my transactions, which needs to be updated. Okay, and it goes to the same. If there are no other processes which are doing this, then this particular process, it becomes the group leader. Okay, if it is a group leader, then it will see that all the other processes, which are in pipeline after a movement, which needs to perform these updates, it will take transactions or sub transactions from all of these, and it will try to do the updates. Okay, and again, as I mentioned that everything happens on the SLRU, the multiple SLRU pages, and if there's a transaction which is working on a different page altogether, if a group update is also performed on a different page altogether, then that actually can go ahead and complete. Yeah, that's pretty much from my side, how CLOG works. Any questions on any of the aspects? Yes.
Well, the group size of the six, the number of things. Can you elaborate on the kind of testing that was performed over there?
Yes, yes. So this goes, all the way back to 2016. Yeah, all the way to 2016 when this was implemented. Okay. So the people who were trying to do this, they tried with lots and lots of numbers. Okay. And then they ran PG bench on it. So when they ran the PG bench, what actually came out is that for more than 5, the log contention was actually significantly high. Either the log contention was significantly high or the disk wasn't, performing, so well. So finally, it's actually less than or equal to 5, but just to be more precise, I'm just saying less than 6. But they found that this is the number which actually makes more sense. And by the way, this is not configurable, this is hard-coded. You can't, tweak it by yourself. Yeah. So PG bench and extremely thorough perf testing, this is how it was actually determined.
Does that mean that this is the average performance or this is like the best performance?
This is the best performance as far as I can tell. Going through all the mailing lists.
Thank you.
Yeah.
We have a lot of sub-transactions spanning multiple pages. How is atomicity guaranteed? Because
Yeah. So say for example, you are on the second page and you subcommitted. Okay, you are on the second page and you are subcommitted. Okay, and my database crashes. Whenever it comes back up again, crash recovery, you see that these were subcommitted, but the parent was never committed. So just throw them out of the box. Very simple heuristics. Yeah, but it is actually possible that your transaction can span across more than 2 pages because there is no upper limit to the number of transactions you can have. Okay. At the end of the day, my parent, it has to be committed. If my parent is committed and everything else is subcommitted, crash recovery can infer that we were we crashed while we were trying to update this page. Any other? Yeah.
So question is like, say, if the concurrent access to these pages is possible, right? Multiple processes can access concurrent.
Yes.
So what are the strategy basically Postgres have taken care in terms of lockings, the techniques you have used?
Yes.
So can you just brief on those, right?
Yes. Okay. So usually, whenever this update happens, lock is you go and tell yesterday, hey, can I update this? That's how you say that, okay, there is no one who is trying to access this page, you can just go ahead. If this condition is not met, then again you have to take a sleepy lock. So again, this is like you just wound up in a loop. As long as you don't get a specific lock on this particular page, you can't just go ahead and commit it. Okay. Again, CLOG does its best, not to just sleep and just wait on things. It tries to do group updates and things like that. But essentially, all of these logs are my LW logs, my lightweight, really lightweight logs. Okay, so yeah. Okay. Any other questions on any of the other aspects? Okay, so a little bit about myself before I wrap up.
I had been introduced to the open source quite earlier on in my life. So I started with Linux in Java when I was in school. I liked the idea of open source, how pretty democratic it was. And I started with Java, and I really liked how the exact JDK code was written. Okay, so that's how I really got interested into computer science in the first place. Okay. So yeah, and I really like to dig into the system, whether I work there or not. That's very secondary. Professionally, I work at Nutanix, where I am responsible for building our own cloud management platform. I won't really go into deep dive into this because no, it's not a marketing talk. Secondly, by my own accord, I'm at least responsible for 5 major production outages, and I have been caught for 4. So one is still no one knows who did this, and I'm on the beat. Best part is after each production outage, I have been promoted. So you can say that things worked out really well for me. Yeah. Thanks. Thank you guys for listening out.